Hello, I'm going to talk about systems, numeric, and conversional codes. First, we're going to start with a little bit of theory to remember everything we already know, and then we start with the conversions, the most fun part. First, we have the binary numeric system. In the binary system, there are only two symbols or possible digit values, 0 and 1. This is because it's a base 2 system. It is used to represent any quantity in decimal or other number systems. It will take a great number of binary digits to express a given quantity, and the binary system is also a positional value system, wherein each binary digit has its own value or weight expressed as a power of 2. Then we have the hexadecimal number system. This system uses a base of 16. It has 16 possible digit symbols, and it uses digits 0 through 9 plus the letters A, B, C, D, E, and F. The GD position are weighted as a power of 16, and the great advantage is that the hexadecimal numbers can be converted easily to and from binary. Then we have the BCD code. This is also called binary coded decimal code. If each digit of a decimal number is represented by its binary equivalent, the result is this code. Since the decimal GD can be as large as 9, 4 bits are required to code each digit. I will put an example later of how to turn a decimal number into this code. Then we have the gray code. This is a non-weighted code that belongs to a class of codes called minimum change codes. Only one bit in the code group changes. In this case, two adjacent code numbers differ from each other by only one bit. In this code is not available in any types of arithmetical operation, but it has common application in analog to digital input-output device. Here are some of the conversions. First, the binary to decimal. This is our binary number. We want to turn it to a decimal number. For me, it's easier to put the number like this. Then we have to multiply it by times 2. And these ones are going to be to the power in a straight order. For example, we start from right to left and we start from 0 until we finish. Then we do the multiplication. I might add that the 2 is the only one that is raised to the power of, not the other ones. We want to select the numbers that are not 0, and then we're going to add them. So, our binary code is equal to 420. Then we have the decimal to hexadecimal conversion. This is one of the easiest. We have the number 1578. We have the binary to gray code. Hopefully you find this information useful. I think that will be all for me. Thank you for your attention, and if you have any other questions, comments, or corrections, we will gladly hear them, and if it's needed, correct it. Thank you.
Now we'll see the basic logic gates. The term gate is used to describe a circuit that performs a basic logic operation. For example, the NOT gate or the inverter. The inverter performs the operation called inversion or complementation. The inverter changes one logic level to the opposite level, meaning in terms of bits, it changes a 0 to a 1 and a 1 to a 0. This is the graphic form of the NOT gate. When a high level is applied to an inverter input, a low level will appear on its output and vice versa, as we can see in the truth table. In Boolean algebra, a variable is designated by a letter. The operation of an inverter can be expressed as follows. If the input variable is called A and the output variable is called X, then X will be equal to A negated. The AND gate. The AND gate is one of the basic gates that can be combined to form any logic function. This gate can have two or more inputs and performs what is known as logical multiplication. An AND gate produces a high output only when all of the inputs are high. When any of the inputs is low, the output is low. Therefore, the basic purpose of an AND gate is to determine when certain conditions are simultaneously true. And this is the truth table for the AND gate. The total number of possible combinations of binary inputs to a gate is determined by the following formula. That is, capital N is equal to number 2 to the n. where capital N is the number of possible input combinations and N is the number of input variables. For example, for two input variables, capital N will be equal to 2 to the second, that is 4 combinations. The OR gate. An OR gate has 2 or more inputs and 1 output, as indicated by the standard logic symbols, where OR gates with 2 inputs are illustrated and it can have any number of inputs greater than 1. An OR gate produces a high on the output when any of the inputs is high. The output is low only when all of the inputs are low. This gate determines when one or more of its inputs are high and produces a high on its output to indicate this condition. This is the truth table for the OR gate. The basic rules for Boolean addition are the following. 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, and 1 plus 1 is equal to 1. And this is the graphical representation. Now the NAND gate. The NAND gate is a popular logic element since it can be used as a universal gate. It can be used in combination to perform the AND, OR, or the inverter operations. The term NAND is a contraction of not AND and implies an AND function with a complemented or inverted output. A NAND produces a low output only when all of the inputs are high. When any of the inputs is low, the output will be high. For the specific case of a 2-input NAND gate, the operation can be stated as follows. For a 2-input NAND gate, output X is low if inputs A and B are high. X is high if either A or B is low, or if both A and B are low. The Boolean expression for the output of a 2-input NAND gate is X is equal to negated A times negated B. Now the NOR gate. The NOR gate is a useful logic element because it can also be used as a universal gate. That is, NOR gates can be used in combination to perform the AND, OR, and inverted operations. The term NOR is a contraction of not OR. A NOR gate produces a low output when any of its inputs is high. Only when all of the inputs are low is the output high. For the specific case of a 2-input NOR gate, the operation can be stated as follows. For a 2-input NOR gate, output X is low if either input A or input B is high, or if both A and B are high. X is high if both A and B are low. The Boolean expression for the output is X is equal to negated A plus negated B. Now we will talk about the exclusive OR and exclusive NOR gates. The exclusive OR and exclusive NOR gates are formed by a combination of other gates. However, because of their fundamental importance in many applications, these gates are often treated as basic logic elements with their own unique symbols. The exclusive OR. The output of an exclusive OR gate is high only when the two inputs are at opposite logical levels. This operation can be stated as follows. For any exclusive OR gate, output X is high if input A is low and input B is high, or if input A is high and input B is low. X is low if A and B are both high or both low. And this is the truth table. Finally, the exclusive NOR gate. The exclusive NOR gate has only two inputs. The bubble on the output indicates that its output is opposite of the XOR gate. When the two input logic levels are opposite, the output of the XNOR is low. The operation can be stated as follows. For an XNOR gate, output X is low if input A is low and input B is high, or if A is high and B is low. X is high if A and B are both high or both low. And here we have the truth table for the exclusive NOR gate.
I'm going to talk about the logic families. To be more concrete, I'm going to talk about the TTL and the TMOS logic families. But first we have to make clear what an integrated circuit is. They are electrical components that are fabricated on a chip. They contain electronic components to construct digital gates inside of them. The gates are interconnected inside of the chip. The chips are mounted on plastic or ceramic container that protects them. The connections are welded into external pins that are ready to be used. The integrated circuits have several pins, and the number of pins may range from 14 on the smaller ones and to several hundreds on the bigger ones. Now I'm going to show you a small picture of the smaller ones, and here is a pictures of the bigger ones. This has a lot of pins. The integrated circuit devices are categorized according to the complexity that they have in their circuits, and also to the scale of integration level. There are 4 types of scale integration level, which are the small scale integration, or the SSI. This one has less than 10 gates inside of them. The medium scale integration, or MSI, has from 10 to 1,000 of gates inside of them. The large scale integration has several thousand of gates. The very large scale integration, or VLSI, has several of thousand, even a million of gates. Now that we know about integrated circuits, let's begin. A digital logic family is the circuit technology that the device has, and it is also important because this helps to classify the type of integrated circuit. The components used to build the technology are commonly used to name the technology itself. The basic circuit followed in each technology is a NAND, NOR, or an inverted gate. Here is a picture of the NOR, and here is a picture of the NAND. The most commonly used digital logic families are the following: the TTL, that is the transistor-transistor logic; the ECL, that uses the emitter-coupled logic; the MLOs, that is the metal oxide semiconductor; and the CMOS. Now I'm going to talk about the TTL and the CMOS digital logic families. Well, the TTL digital logic family is considered as the standard because it has been used for 50 years, for more than 50 years, and it is like a lifetime. Although the TTL is nowadays obsolete, the standard is nowadays obsolete, and the newer families are being used properly. On the other hand, the CMOS family has become one of the most used integrated circuits because they don't use a lot of power. It means that they don't require a lot of power.